We should be recording. Can everybody see my screen?
Yes, we can see your screen.
Okay. So, a quick recap from the first lecture. It was pretty short. We basically went over some vocab. We wanted to know, what is a computer algorithm? What is a computer? What is an algorithm? And then we, at the very end, we introduced the concept of a computational gate. So the gates that you see underneath the header of task 1 are called logic gates. And these are the fundamental, when we talk about an algorithm as something that manipulates information, these logic gates are the basic building blocks, the atoms that make up the universe of computing. And what we are going to talk about today, first off, did anybody attempt this homework problem? Anybody try it out? Was anybody curious about how it goes? Jackie, go ahead.
I tried it out and I made an algorithm for it. And do you want to hear it?
Sure. How did it work?
So I wrote down initialize a result variable to 0, then add the x value to the result and repeat y times. And then at the end, the sum is the product of x times y.
So
I don't know if I did it right.
You basically added x to itself y times. Sorry, I've got a little bit of a lag going. Let me see if I can share my screen, and then we can look at a diagram. Because the whole point of this, and can folks still see my screen? So it should show the homework problem right now. The whole
Yes.
point of this homework problem was to get us all familiar with, comfortable with the idea of representing an algorithm with a picture. And so that's what we were trying to accomplish here. So Jackie, you were just saying you started off with a register at 0?
Yes.
So talk me through it one more time. Let's draw it together.
So we start off with 0, and then you would start adding x to the register with 0.
Okay. This makes a register
And then,
starting in x. So the output here is x.
yes. And then we would repeat it y times.
That's good. I'm going to draw it a slightly different way, but I know exactly what you're saying. So start with x. Maybe, yeah, here we go. Like this?
Yeah, I think so.
So when you use the addition unit once more, now you get x plus x. So that's just 2x. And what we want is yx. So you're exactly right. You just repeat this y times. Or I guess if you've already done it once, y minus 1 times. But the rough idea is you start with y x's, and you add a to them in this kind of descending pattern, so that by the time you get to the bottom, you've added x to itself y times, which is the definition of multiplication. That's perfect. Very good. Okay. Did other people get that, or any questions about this before we get into the meat for lecture 2? Cool. Well, so we're going to get into using these logic gates and understanding how they manipulate information. So just recap the definition of a classical algorithm. It's a set of gates or series of steps. The gates are the smallest steps that take in some set of bits and spit out some other set of bits. That's all computing is. And so we want to define in this lecture how to build a quantum algorithm. And to do that, we need to dig in a little bit more into these classical gates because they'll turn out to be quite helpful. So first off, we're going to do an exercise where I'm going to take this logic gate in the top left. This is the circuit representation for a NOT gate. And I'm going to introduce a different representation. So I'm just going to represent it as a box with an X in it. And the X is representative of bit flip or NOT. And in the last lecture, we went over what happens when you put a 0 into an X gate. Can somebody tell me what it outputs?
It would be 1, right?
Yep. And what happens if you put a 1 into an X gate?
0.
Cool. So in the top right, you can see we've got this truth table that fully defines how a NOT gate operates on bits. 0 to 1, 1 to 0. Pretty simple. Now let's look at the XOR gate. So I'm going to, again, introduce this representation. Notice that the XOR gate is similar to the X gate. It has this little wire coming out of the top with a little black circle connecting to a different bit. And what we call this little black circle is we call it a control. So the way to imagine how this gate works is when the top bit is 1, we perform a NOT gate that we just looked at on the bottom qubit. And when the top bit is 0, we do not perform a NOT gate on the bottom bit. So if I put in, and also the control does not change the value of the top qubit. So if you see here on the diagram, I've already filled in that 0 comes in on the top and 0 comes out on the right. So the real thing that we need to figure out is, I've just told you the answer, but what happens when you put 0, 0 corresponding to the top row of this truth table? What happens when you put 0, 0 into this control NOT gate? What comes out in the bottom? Is it a 0 or a 1?
It would be a 0.
Correct. So you see now in the Q column, I'm filling in that truth table. Let's do a couple more of these. What happens if I put a 1 in the bottom where the top is 0?
0.
So a 1 comes in the bottom, and the claim is it turns into a 0.
Yes, because it doesn't reach the initial condition.
Do other people agree, disagree? So we defined, remember what the control's job is. The control, it says if the top bit is a 0, then we don't perform a bit flip on the bottom qubit. So in fact, this would actually just remain a 1. So again, nothing happened. As long as the top bit is 0, a 0 goes to a 0 and a 1 goes to a 1. So what happens if the top bit is a 1? Pavel?
I think it's 0.
Good. Well, so the top bit is a 1 and a 0 is going in on the bottom. So what should come out on the right?
It's gonna be 0.
Do other people agree, disagree?
I think it might be a 1.
How come?
Since it's a 1, we are performing the NOT. So
Because
we would,
yeah,
the top is 1.
So because the top bit is 1, the control says activate the NOT gate. So the bottom qubit will get flipped. And if the control bit is a 1 and the target is a 1, it ends up being a 0. So this one had a couple curveballs in here. It's important to understand how this control works. But so far, I'm still just talking you through how classical computing goes. So just a note on notation. I'm writing a NOT gate with a control to an X. In the industry, in quantum, we write it with a little plus, like a little target symbol. It's just, I don't know. That's what people ended up deciding to use. It's just a note on the notation. if you see a circle plus with a control, it's a control knot. That you'll see that more often than you see a control leading to an X gate. So let's actually now get into some quantum stuff, because so far, I mean, I'm giving you this little notation, like the little arrow around the 1 and the 0. That's technically quantum notation, but I haven't actually given you any quantum concepts yet. So let's get into the quantum realm. And the whole thing I want you to remember is that quantum is not inherently harder or more complicated or more difficult to understand than anything else. The only thing you have to keep in mind is just that quantum is different than most, if not every other thing you've seen before. So if you leave some of your preconceptions at the door and are open to things getting weird, quantum will fit right in. So we are going to enter the quantum realm with the two gates that we have just spent a lot of time trying to understand. The bit flip that just swaps a 0 to a 1, and the control bit flip. So the idea of adding a control to a gate and only doing the action if the control was a 1 or a 0. This whole lecture series has been building from the first thing we looked at to the NAND game, where we were showing how you build these logic gates from basic circuit components, to we've just talked about the bit flip gate. And now we're going to understand that when you use these gates to build algorithms, everything can be made from a bit flip gate. If you start with the component on the left, you can make a NOT gate. And if you go through the levels of the NAND game, you can build the AND, the NAND, the OR, the XOR. You can build them from the NOT gate. So in a way, if you just allow the ability to add controls and to put things together, all of classical computing is just one gate applied in fancy ways. And I've said this before, but the whole adage of if you let a monkey sit on a typewriter for infinite time, they'll write Shakespeare. People heard this. So the joke is, if I trapped one of you in a room for infinite time with nothing but a NOT gate, you would come up with every computer program possible, every computer game, every app, every single program that a computer can run comes from this one gate and adding controls to that gate. When we move into the quantum realm, we now have to allow for new types of operations on our information, not just flipping bits or control flipping bits. Now we have the ability to do fundamentally new things that are fundamentally quantum things to our information, like performing superposition or phase rotation or creating entanglement. So we're going to talk a little bit about how those things work, and feel free, again, as always, stop me with questions. But we're going to have some fun here. So let's just go to our typical format, definitions. What is a quantum algorithm? It's just a series of steps, and you allow for a wider set of fundamental gates than just a bit flip. So what you have on the right is an example of a quantum circuit. The Q0 through Q1, Q2, Q3, Q4, those are the bits. And H is a 1-bit operation that does something. And you've got a lot of control bits or XORs. So that's a classical operation put into a quantum circuit. And this circuit doesn't do anything. It's just intended to show you some of the language, some of the structure. You've got vertical layers, and each gate that occurs in the same layer, so these H gates in the green, those are happening at the same time. And gates which are to the right of that happen at a later time. So it's basically a way of showing qubits arranged in space and which algorithms and in which order, which gates and in which order you're going to perform. So again, it's just this diagrammatic way we've been building toward of showing you an algorithm by showing you what steps to perform on what bit and in what order. Questions? I'm going to pause here.
What is T stays for?
We
Yeah,
will get to
so
T.
H is...
But so yeah, I haven't defined T or H yet. We will get there. H is called the Hadamard gate. And what H does is it takes a bit that's either a 0 or a 1, and it creates a new type of information that's statistical. It creates an equal probability of 1 or 0 called a superposition. So H is the superposition gate. So back here in this little diagram, the red circle for superposition, H could be thought of as the canonical superposition gate. So it's bringing in the quantum phenomenon of superposition. Now, I'm not telling you why it's doing that or how superposition helps. That's stuff, we could get to. But that's what it's doing there. And then T is the corresponding to the blue circle. It's a phase rotation. And again, I haven't told you what that means or why it's important. We'll get to that. And then finally, the 2-qubit gate, the XOR that we knew before as a classical gate, when you bring it into the quantum realm and put quantum information into the control bit, you get some really interesting things happening. And in fact, you can use it to generate entanglement. And that's the punchline at the end of this lecture. We will get to trying to leverage a thought experiment that helps us understand how that works. Okay. But the basic takeaway from this slide, all I'm trying to get you to understand is that quantum algorithms are just like classical algorithms. The only difference is they have a larger vocabulary, a wider alphabet of possible things you could do to the information. And all we have to do is see some examples of how those new things might be beneficial. Okay, so as we talk about quantum algorithms, quantum computing, we can't have this conversation without talking about quantum information, or what I like to call non-binary information, because all of our computers run on binary. So what does non-binary information look like? And just think, go back to, this is the model for regular computing. Again, I lock one of you in a room. All you can do is use an X gate to flip a 0 to a 1. And control whether or not you do that on the value of other bits. This back and forth, that is all classical computing. That's all it is right there. So then how do we talk about things that are not binary? Does anybody have some examples of, what word or model do people use when they typically talk about things which are more than just a 0 or a 1?
Hexadecimal.
Hexadecimal. Jackie, what did you say?
Is it like decimal?
Yeah, so you're both thinking like other bases. So binary is a counting system. It's just a counting system that uses 2 numbers. Abby brought up hexadecimal. That is a counting system that uses more than 2 numbers. So those are possible, but we're trying to get to something like beyond discrete counting systems. So we're not so much going to be thinking about ways to count using an X number of symbols. The thing I was hoping somebody might mention is anytime I hear about people talk about something that's non-binary, they're like, well, it's on a spectrum. There's a spectrum between 0 and 1. And things which can have a spectrum between 0 and 1, they actually do have a place in computing. I'm not a specialist on this, but I do remember reading something about fuzzy logic, which I think uses spectrums of values between 0 and 1 in computing. Don't quote me on that. You can Google it. But I brought this up because, you can express things which are between 0 and 1, but this isn't actually the model we're going to use for quantum. I find this basic. Instead, we're going to use something kind of cool. In fact, what we're going to see is that non-binary information, quantum information, the smallest, bit of information that you can have in quantum can be visualized as all of the points on a sphere, where you've got your 0 and your 1, where 0 is the North Pole and 1 is the South Pole. So you can still apply bit flips on a qubit. This sphere is the block sphere representation of a qubit. So you can perform bit flips on a qubit. And so you can see how before we had just flipping between 2 discrete states, and that gives you all of regular computing. You can see now how, if you just restrict yourself to the same subset of those gates, you can have all the same capabilities with a qubit. You wouldn't want to do that for engineering reasons, but the point is that the sphere has everything the classical world has contained within it and more. So the we're going to need new operations, not just operations that send us from the North to the South Pole, but in fact, we're going to define a set of new logic gates, which we'll call quantum gates, which can get you any point on the globe. And we're going to do that with rotation gates. So Rx is, if you see the big symbol X on the globe, you see it's this kind of horizontal +1 diagonal axis right here. We could rotate our blue dot around that axis, or you could think of holding a ball and rotating the ball around that axis as one operation. And you can rotate about any of the X, Y, or Z axes. And the punchline is that because you actually only need 2 axes of rotation to get every possible state. But this is maybe a more complete set of gates. So what I'm saying here is that before, all we needed was a bit flip gate to get all of the possible bit states. They're just 0 and 1. And now, if we want any possible qubit state, we can express it through rotations around particular axes by particular angles. So just a quick note on notation. So if you want to express, instead of, you've got your 0 and your 1 that you express for the top or the bottom of the sphere, if you want to have any arbitrary point on the sphere, we'll use the Greek letter psi. It's just like an unknown solved for X type of thing. I'm just representing all of the possible states. I might not know which one right now as psi. I'm going to stop there. Questions?
How many options are possible for theta? If it's X, Y, and Z, or that.
Yeah,
How many
anything.
options?
Basically, I mean, if you're in degrees, anything from 0 to 360. If you're in radians, anything from 0 to 2 pi.
So we have like 360, 360, and 360. So it says.
You've got full rotation capabilities around any axis. And one of the warm-up problems that I uploaded to the GitHub to get people prepared for the challenge is one where you will actually have to find the optimal rotations, the optimal angles. You'll have to find a particular quantum state that maximizes or minimizes a function. So you can think of these angles as variables, where maybe you don't know which qubit you need. Maybe you don't know which quantum state you need for your problem. And that's actually the framework that both of the NVIDIA challenges are cast in. We have this challenge where we might not know beforehand which state we need our qubit in, or our qubits in. And so the program is to write a circuit with these rotations and then use some optimization software, use some machine learning to figure out the correct angles that we need for the particular application. And I can get to that more later on. But the reason I'm giving you these rotations as your first look at quantum gates, because there are quantum gates that don't have angles in them, is so that you can start thinking in the terms that you'll need for the NVIDIA Hackathon challenges. Okay, so we started this lecture with some exercises, understanding what what the effect of a gate was on an input bit. So now I've got a little problem for you. Which axis and by what angle do we need to rotate to send a point on the North Pole to a point on the South Pole?
Thing is, so would it be like 180?
Around what axis?
I want to say the Z.
So rotating around the z-axis means that points that are on the z-axis stay still. So z is actually the only axis we can't use here. But 180 is the correct angle, yes. Or pi, if you want to do radians.
So would it just be X and Y that we used to get to
Yep.
1?
Both of those will work. If you rotate around the x-axis, it'll send it around the globe in one direction. Rotate around the y-axis, it'll send it around the globe in the other direction. It's like saying, how many different ways are there to get to the South Pole from the North Pole? There's a lot of different ways. So we're just looking at the two kind of core ones. And yeah, so if you do an r of x, a rotation around the x-axis, and you put pi in for the angle, you would send 0 to 1. So that's your first quantum algorithm. You did it. Wasn't that hard?
Could the 180 also be negative per se, like going in the
Yes.
opposite direction?
10,000%. Pi is equal to negative pi if you're rotating. That's not true for pi over 2 and negative pi over 2, because that'll send you to two different sides of the globe. But if you're doing a 180-degree rotation, that's the same as a negative 180-degree rotation. Great observation, Abby. Okay, so we are gonna it's a little bit of a little dorky, but we're gonna think about this globe like something like I was just at a barbecue place the other day, and they had like the number that they gave us for our table had a particular section of the cow and the name of it, and that's how people found our order, delivered our order. So we're gonna carve up this block sphere, and we're gonna identify the parts of it that have different properties to others, because you can look at the thing on the right and we can actually find a lot of the parts of quantum information, the parts that are in superposition, the parts that have phase. We can find them on the block sphere. So if we have a point on the North Pole, again, we're going to start on the North Pole. Most algorithms start off all their qubits in the 0 state. And we perform all of the x rotations. So all of the rotations around the x-axis. Well, actually, I'm going to back up for a second. I got ahead of myself. We're going to start with a point on the North Pole, and we're going to go back to this bit flip possibility. So it can send it to the North or the South Pole. So in this picture, you've got actually 4 circles. You've got the yellow, red, blue, and then black. And the black is just classical computing, like we talked about before. So the North and the South Pole, toggling between those with an X gate, that's just classical information, classical computing. If you have a Y rotation, so you're doing every single rotation, 0 through 360, and you're looking at what are all of those quantum states, psi, what do they all have in common? They all have in common that they are in a superposition. Now, what does that mean? People have heard of Schrodinger's cat? Somebody tell me what the deal is with Schrodinger's cat.
It's
It's a
existing,
cat that's
doesn't
alive and not alive, right?
Yes. So this is Rem. He's alive, and he's quite a pest. If people can see my camera, I'm holding my cat up. But the idea is something that's in superposition occupies a new kind of existence that isn't alive, and it isn't dead, and it isn't in between. It's in superposition. And materially, the effect that this has is when you look into the box, you see alive or dead with some probability. You see 1 or a 0 with some probability. So can someone tell me, then if I wanted a cat that's equally likely to be alive and dead, I would want a point halfway between 0 and 1 on this blue circle. So that's a point on the equator, on the horizontal, like the widest part of the circle. And if I move that point closer to the 0, what does that do to my probabilities? What's more likely, 0 or 1?
0.
0 is more likely if you're closer to 0. And if you move it closer to 1, 1 is more likely. So superposition, you can kind of think maybe there's some use for this. If you have now the ability to build statistics and probability into your computer at the basic bit level, that's kind of cool. And in fact, that's warm-up challenge number 1. I show you how to make a superposition gate that just makes equal superpositions, just even 50-50, and then shows you how to write a program. For warm-up challenge 1, you're going to write a program that just gives you a random number generator. Now that's actually, there's a quantum startup that's built on that idea. That's it. If you have a classical random number generator, like in your Python, you can do random, there's all sorts of random packages. What you'll learn in computer science is that those functions are called pseudo-random. They're faking being random because classical information doesn't know how to be naturally random in the way that quantum information does. So that quantum certified randomness gives you the ability to give perfectly random numbers, and then that gives you the ability to sell those random numbers to anybody building a software based on randomness they don't want to be hacked, like a casino game. If somebody has quantum numbers at the core of their digital casino game, it's impossible to predict what the next outcome will be, certified by quantum physics. So the equal superposition line is very important, very helpful. And that Hadamard gate we talked about before, the H gate, that's the gate you'll be using in warm-up challenge 1. Okay, so I notice we're getting close to time, so we're close to the end of this. So I'll just kind of go through the next ones. So let's stay at the equator. I like the equator. If I'm at the North Pole, I can't actually talk about phase because phase requires z rotations. And as we just talked about, if you're at the North Pole, you apply a z rotation, nothing happens. And that actually tells you something nice. If you apply a z rotation to 0 or 1, you just get 0 or 1. It doesn't do anything to them. So we're going to do a pi/2, which sends us to the equator. A pi/2 y rotation sends us to that point on the equator we were just talking about. And now I'm going to look at all of the possible z rotations. The first point has just superposition and no phase. That's why I showed it as just a red circle. But every point on this equator is equal superposition. What differentiates them is now they have a phase rotation. So this first point by the y, that is 90 degrees, or pi/2. The point on the back there is 180 degrees away from x. That's pi. And you wonder, like, well, what's the point of phase rotation? And it's a deep question. One easy way to think about it is if you could toggle between the x phase and the 180 degrees back from it, that's kind of like toggling from the 0 to the 1 state. So there's this weird property that you can encode information into this phase space that now lives only in the quantum realm. You can't see it in the classical realm. It doesn't affect the measurement probabilities. So even if you stored a bit in your qubit on this equator, you would still have a 50-50 chance of seeing 1 or 0. But because now you have this extra dimensionality to encode information, now you can do more sophisticated or interesting things when you send that phase information through a quantum circuit. Another way people try to explain it is talking about interference. They say if you've got phase, what that means is your qubits can interfere with each other. And the hand-wavy, I don't like this description, but the hand-wavy description quantum algorithms people will use to describe why that's helpful is you could make positive interference where the correct answer is a negative interference where the wrong answer is. It's kind of hand-wavy, but anyway. So quick note on notation, you won't really need this for warm-up challenge 1 because the Hadamard gate is just got its own command. You won't need rotations to express it, but you can express the Hadamard gate as 2 rotations. First you get down to the equator with a pi/2 y rotation, and then you go to the back with that X rotation around pi. Anyway, you'll need the Hadamard gate to make the random number generator in warm-up challenge 1. This is the last thing I wanted to get to. We just talked about how you can carve up this qubit and you can find in superposition states. You can find superposition states with phase in them, which is crazy and interesting. But where are the entangled states? Does anybody have a guess or a thought or a question about nothing related to this?
Do the qubits have the same size?
Pardon?
Qubits, do they have the same size? Are they equal in size, or they
Yeah.
different in size?
We can consider the block spheres of 2 qubits to be identical. The punchline is you need more than 1 qubit to make entanglement. 1 qubit has no ability to entangle. You need more than 1. Entanglement is like a relationship type of thing. So let's make some entanglement. And we are going back to the XOR gate we started with. So we just went over what happens when you feed a 0 or a 1 or, 0, 0, 1, 1, 0, 1, 1, 0. All the bits, we know what happens when you put a bit into an XOR gate. But now notice that the control, I'm not feeding you a bit. I'm feeding you that 0 phase equal superposition quantum state, which means you have this bit that you're feeding into the control, where the control needs to know if it's a 0, I do nothing. If it's a 1, I do something. And this bit is saying yes. It's saying Schrodinger's cat. It's saying quantum yes and no. So what happens? What does the bottom state turn into? And we're at time. So that's just a brain tickler for next time. I'm going to stop there.